Hey guys, Mr. Delos here, and I'm going to talk to you about some physics. Specifically, we're going to talk about linear motion. Well, ironically, that's not what this guy's about to do. He's actually a projectile at that moment in time once gravity is the only thing affecting him. But we'll talk more about that in the next unit. So let's go ahead and dive right into some content here. So we have reference frame and reference points. Let me kind of start off by talking about these things in this regard. So from a global standpoint, the surface of the Earth, we have two reference points. We have the equator and the prime meridian, right? We have prime meridian here and the equator here. And so those would be our reference points for the two-dimensional space that is the Earth. The reference frame would be the fact that as you go up, that would be the north direction versus down being the south direction. And that's, all dependent on how you have yourself oriented. And that's part of the reference frame, that we have that directionality that we can all agree on. That's part of the reference frame. But another aspect of reference frame would be, as an example, you are on a train that's moving 100 miles per hour, and you are running on that train towards the front at 5 miles per hour. How fast are you moving? Well, that depends. Typically, and the assumed answer there would be 105 miles per hour relative to the ground, some stationary observer that's on the ground. But relative to somebody who's on the train, you're just moving the 5 miles per hour. And so that would be a reference frame issue. Are you on something that is rotating, and which often becomes an issue with reference frames, and we'll get into that more later in the year. So reference frames generally will have an issue of like, are you in a moving reference frame? Are you moving right now? And you might say no, but I also might say yes, because you're on this giant globe spinny thingy that's hurtling through space at thousands of miles per hour. And so you are moving relative to something, to Mars or some fixed arbitrary point in space. But relative to the wall next to you, no, you might not be moving. So it is a reference frame issue that we'll get into more later. Scalar versus vector quantities. So a scalar quantity is one that does not have direction. It has magnitude only. Magnitude meaning size. A vector quantity is one that has both magnitude and direction. So a scalar quantity might be like the Richter scale being what measures earthquakes, so how much vibration there is. And you can't have a negative amount of vibration because you're just concerned about how much there is, the size of it. Vector, however, could be something that does have a concern about direction. So let me see if I can make a straight line here with a 0 position, a 1 and a 2, and a -1 and a -2. So I've just got a number line here. And so, and in fact, what I'm going to do is I'm going to just mess it all up. So what I'm going to do, I'm going to take all this stuff, and I'm going to copy all that. Hopefully it copied everything. Yeah, okay. So I'm going to keep using this. And so here's what's going to happen. So here's my example of something that is a vector. Maybe I have something that is going to move from the 0 position to the +2 position. And then I have something that's going to move from the +2 back to the 0. And so the direction matters here in this particular example. In some cases, the direction doesn't matter. So a vector is something that has both magnitude and direction, and we will often represent vectors with arrows like this, where the size of the arrow represents the magnitude, and of course the direction of the arrow represents the direction of the vector. So we have position, of which I was actually just talking about, and from context I'm sure that you have a good idea of what's going on. So as an example, let's say that I have a position that starts here at the -2. And so I go to the +2. I did have a position at the -2. I now have a position at the +2, and there's of course a difference between those two. The difference would be your distance. However, let me continue that a little bit. What if then you went back to your original location? So you went 4 meters to the right in a positive direction, and then you went 4 meters to the left in a negative direction. The distance that you traveled would be 8 meters, right? 4 to the right, 4 to the left, you'd have 8 total. That is your distance traveled. Direction is irrelevant for distance. It is a scalar quantity. Displacement, however, is a vector quantity. Let me see if I can paste this thing in one more time. And in fact, I really like this color. I'm going to stick with this color. And so again, let's stick with this example. We're going to go from the -2 to the +2 and then back again to the -2. So while the distance would be 8, right, 4 this way, 4 that way, in total you traveled 8 meters. No regard to the direction. Your displacement, however, would be different. Your displacement takes into account where you are and where you started only, and anything that happened in between doesn't matter. So here are the 3 equations, 3 different versions that you might see of really just they're all the same equation. This here is the delta symbol. It means change, the change in something, so the change in position. So the letter D, lowercase d specifically, is going to represent position. Not distance, not displacement. Sorry, I didn't make it up. It's not my fault. This is the way that your textbook will typically represent it. Unless I give you some worksheets where a higher level textbook might have an X. This is actually my preferred way because this specifically means that you're moving along the X-axis. You might see an example where if something is falling, we might use the letter Y to represent its position along this path. So you might see the letter X being used, but I digress. So let's just assume we're using this for the moment. You have your second position, right? This subscript refers to more information on this variable. This is your first position, or this would be your final position and initial position. But in either case, you have your last spot minus your first spot. So last spot, first spot, and the difference between the two is actually 0 in this case. So you started and finished in the same spot just like you would if you were in NASCAR where they don't really go anywhere, right? During a NASCAR race, their displacement is 0. They finish and start in the same spot. They just make left turns all day long, and good for you. So displacement in this case would be 0. Let me give you another quick little example. Let me kind of erase, see if I can do this neatly. Oh, all right. And so give another example where maybe I start at the -1 and I go to the +2, and then from there you go back 1. So what is your displacement and how would you represent it? Well, the resultant vector would actually go from the very beginning to the very end, just like that. And it should have the length representing the direction and magnitude. So it goes 1, 2 to the right, and that is a +2 displacement. That is your resultant. So the displacement is the resultant of your change in position. Let's look at some other examples of a resultant vector. So here I've got this guy flying a plane. This is my good friend. His name's Todd, right? So Todd is flying off in a east direction at, let's make something that you guys would know. Let's just make it 100 miles per hour. Usually we might use meters per second, but for right now I'll just use some units that you can imagine. So he's moving at 100 miles per hour, and let's say he's going into a headwind that is 50 miles per hour. And so it'd be represented like this, where I should make this one about half the length of that. And my resultant vector should go from the very beginning, it should be lined up with it, go from the very beginning to the very end, and it should look something like that. And it will have a value of 50 miles per hour, but specifically a positive 50 miles per hour, because this one was a negative. Relatively speaking, if this is a positive direction, this is relatively speaking a negative direction, and your resultant will be a positive 50 miles per hour. You could also do, let's say he's traveling, you know what, I'll erase these. He's moving east at 100 miles per hour, but instead of it being a headwind, let's say that it is instead a crosswind of 100 miles per hour. And so the resultant would go from the very beginning to the very end, something like that. And the length of this, right, this is the hypotenuse of the triangle, Pythagorean theorem, a squared plus b squared equals c squared. The length of this would give you the his speed relative to the ground. So relative to the ground, he'd be moving at, and I don't remember exactly what that is, but I want to say it's be like about 150 or so, give or take. And so that's an example. We'll get more into this two-dimensional aspect in the next unit. So relative motion, as I was saying before, it's everything's motion is relative to something else, and then it's always something to kind of keep in mind because it can kind of trip you up sometimes. We usually try to make it a stationary reference point, but we can't always do that. So just another example, you're on a train going 60 miles per hour, and you walk towards the front going 5 miles per hour. Of course, you're going towards the front, which means that these two will add together. All right, we have 60 plus an additional 5, and that would give us a complete total. Oh, that was a little ugly. Right, go like that. So 65 miles per hour total. Ignore that one. So let's talk about speed. So from context, I'm sure you have an idea what speed is. It is how much the distance changes per time. It's how quickly you're moving. But it is a scalar quantity. It is scalar. Direction doesn't matter. You have a speedometer in your car. It measures the speed of the car, regardless of direction. Okay? Speed is scalar. However, a vector quantity would be velocity. So velocity is essentially the same thing as speed, except you have to account for the direction as well as just the speed. So it's how much your position changes, or your displacement during that time, and your velocity is essentially, sorry that I've got this written out, a little too mathy looking, but basically what it comes down to is the velocity is displacement per time, the change in position per time. So this is also the way that speed will also be represented. Velocity or speed doesn't matter. We really kind of use the same equation. You just have to keep in mind if direction matters or not. And so that is velocity. How quickly you're moving, but in the direction you're moving as well is relevant. Acceleration is equal to the change in velocity divided by the time it takes to do that. And so let's say we go from 30 to 60 meters per second. And so if you're going from 30 to 60 meters per second, it'd be your final minus the initial. That's a change of 30, a positive 30 specifically. So you're looking at a change of 30 meters per second. And you, let's say, go from 30 to 60 meters per second in a time of just 3 seconds. So divide it by a time of 3 seconds. Your units are meters per second per second. I would like to put parentheses around this part so that way you can express that this is meters per second per second. And what does that mean? It means that you've changed your velocity by 30 meters per second in a time of 3 seconds. So what is this equal to? This is equal to 10 meters per second. Again, I'm going to leave the units like this. So for every 1 second that went by, you changed your velocity by 10 meters per second. This is mathematically the same thing as 10 meters per second squared, and this is usually the way that we will represent it. Okay, so that is acceleration. And what else about acceleration? Let's see, how can you accelerate? You can either accelerate by speeding up, slowing down, or changing direction. So when driving a car, you actually have 3 different ways to accelerate. You can hit the gas pedal, hit the brake pedal, or turn the steering wheel. In fact, what if you decided to have a little party in the back of an 18-wheeler big truck, and your guys are going down the road, it's a motorhome, something like that, and all of a sudden, you black out all the windows, all of a sudden everybody hits one side of the inside of the 18-wheeler truck, and everybody would just assume that the truck driver had hit the brakes, but that's not necessarily true. He could have hit the gas. So what if you're going in that direction and you hit the gas, then the back of the truck would accelerate into you, and it would be the same thing as if you were going that way and you hit the brakes. So in either case, he would hit the same wall. Or what if he was coming towards you, he turns in that direction, the wall would accelerate into your path, and you would still hit that wall. So in all three cases, you would perceive those things to be exactly the same. And then we've got these three equations that will be really relevant to us. The velocity here is an instantaneous velocity at a specific moment. It's not average. At a specific moment in time, you have reached this velocity. So if you accelerate at a certain rate for a certain amount of time, at the end of all that, you will reach this velocity. If you are accelerating due to gravity specifically, so you have an object and you drop it and it falls, it will fall at 9.8 meters per second squared. That will be the rate at which it falls. So that means that after 1 second of free fall, at that moment, it will have a velocity of about 9.8 meters per second. And this is pretty close to 10. So we're going to round that off to 10 meters per second. So we're going to round that off to 10 meters per second, and we're going to generally use that as our acceleration of gravity. Unless we're doing an actual lab, we'll just use 10. So after 1 second of free fall, an object will be moving 10 meters per second. After it's in free fall for 2 seconds, it will be moving 20 meters per second, and so on. And then let's look at this one. This refers to how far an object will fall, given that it's falling for a certain amount of time and that it's actually experiencing the acceleration of gravity. Or it could be any other acceleration. We just use the letter G for that acceleration when it is falling specifically. But it doesn't have to be falling. It could be accelerating to the left or right because it's a car or whatever it might be. And so in this case, it's accelerating. Let's just say it is gravity. It's accelerating at 10 meters per second squared. Oops, forgot the squared there. For a time of, let's say, 1 second. What would be the distance that it fell? So if it's moving, accelerating at 10 meters per second squared, and it falls for 1 second, let's say 1 squared times 10. Okay, so 5. It would have fallen 5 meters in that first second. What about after 2 seconds? 2 squared, 4, 40, okay, 20. So this would have fallen 20 meters. What about 3 seconds? 45. So it goes from 5 to 20 to 45 meters. Notice how there's that exponential increase as time progresses because it's squared. So your displacement will increase as time progresses. So these three equations, really it's just two equations, will be useful to us as things undergo a constant acceleration. It's not always going to be 10 meters per second squared, not always. But if the object is just simply falling under the power of gravity, then yes, we will use 10 meters per second squared as the acceleration, and we'll just kind of plug that in to figure out how fast it was going by the time it all was said and done, or how far it went by the time all was said and done. And that's going to do it for this one. And I appreciate you watching. You guys have a good one. You guys take care.